Professor Dr. N. Ganesh is working as a senior faculty, Department of Computer Science and Engineering, SRM University, City Campus, Vadapalani, Chennai. He has more than 12 years of undergraduate and postgraduate teaching experience, which includes 5 years of research experience. He has trained many corporate batches on technologies such as mainframes, Application Systems 400, SAP, ABAP. He has published 10 articles in both international and national journals. He has presented several papers in both national and international conferences. He has written 4 books which are prescribed in Anna University affiliated colleges, SRM University and Bharat University. His research interests are software engineering, data mining and cloud computing.
Welcome to UGC lecture series in computer science. We are going to see about the subject operating systems. For the semester 5, it belongs to paper 8 of the undergraduate degree program, in which in today's session we have the unit 2. In the unit 2, we have topics such as process synchronization, critical section problem, synchronization hardware, semaphores, classical problems of synchronization, critical region monitors, deadlock characterization, methods for handling deadlocks, deadlock prevention, avoidance, detection and recovery. This is full of unit 2, out of which we are going to see the topic on deadlocks. This deadlock topic will be carried out in 2 different sessions, out of which we will be moving on to the first session of deadlock. Today's content will be deadlock and overview, characteristics of deadlock, types of deadlock, how to deal with deadlocks, ostrich approach, necessary conditions for deadlock. What is a deadlock? In a computer system, deadlock arises when members of a group of processes which hold resources are blocked indefinitely from access to resources held by other processes within the group. A deadlock is a situation in which 2 or more competing actions are each waiting for the others to finish and thus neither ever does. Fine. What are the characteristics of a deadlock? For a permanent blocking of a set of processes that either complete for system resources or communicate with each other, no efficient solutions, involve conflicting needs for resources by 2 or more processes. Let us look at a real-time example that we face in our day-to-day life. You might be aware of the traffic scenarios that happen in and around the city. In this slide, you could find the buses and the cars are waiting in a queue, wherein the cars are not able to move from one point to another. So this is a situation that we face in our daily life, and this is an example, real-time example for a deadlock. Even in this slide, you have the cars which has been placed haphazardly, wherein it does not allow the truck to move from this particular point to other. Let us relate with an example that coordinates or that corresponds to the computer system, wherein here in this example, in this slide, you could find 3 different resources and 3 different requests. So the process A, it requests for resource R, and you have 3 different processes named A, B and C. When A requests for R, same time the B requests for S and C requests for T, that you could see in this diagram. Then at the second instance, A requests for S. So wherein this S has been occupied by this B, and at the second instance B requests for T, wherein B is being occupied by C, and at the third instance C is requesting for R, which is available over here. So here this is a situation for a deadlock. See, this resource is being held by this particular process. So if I want to have a situation wherein if there is no need to have a deadlock, then either of the resource should get relieved and this process should relieve the resources. So let us consider the next slide. In this slide, A requests R, resource R, and C requests the resource T, and A as well requests the resource S. C requests the resource R. A releases R. So this resource was being used by A, and now this particular resource is being released by A. So A has released this resource, that you can see in point number 5. Now again A releases this S as well. So if the C has requested for the resource R. Now since A has released this resource S, R as well S, now this C can take over this resource R. So here in this slide there is no deadlock, wherein in the previous slide you could have seen the deadlock condition. Now let us proceed to the types of deadlocks. There are two types of deadlocks. One is resource deadlock, other one is communication deadlock. What is a resource deadlock? A resource deadlock uses AND condition. AND is, why it has been put in capital letters is, it uses the logical AND, wherein a process that requires resources for execution can proceed when it has acquired all those resources. Whatever available resources in and around that particular process, it will be acquiring all those resources. So such a condition is called as a resource deadlock. And next is the communication deadlock. Here it uses the logical OR condition. So if it could have either one of the resource, then it can proceed for an execution. So it requires at least one execution in order to which is being acquired least one of those resources. What are the types of resources? Again, now in the previous slide we have seen about the types of deadlocks. Now we are going to see about the types of resources. So again, the types of resources is being classified into two types. One is reusable resource, other one is consumable resource. What is a reusable resource? Reusable resource is one which is being used by only one process at a time and it is not depleted on that use. What do you mean by a consumable resource? A consumable resource, it can be created and it can be destroyed. Created is nothing but it can be produced and then it can be, after usage, it can be consumed. So producing and consuming. I suppose you would have seen this concept in your previous lectures. Then how to deal with deadlocks? There are three different approaches in dealing with deadlocks. One is the reactive approach, second one is the proactive approach, third one is just to ignore the problem. So now what do you mean by a reactive approach? A reactive approach is before an event happens, how do I protect myself? How do I protect my system? That is called as a reactive approach. Now how do I deal with this kind of approach? Here we need to have a periodical check of events whether any kind of deadlock happens or not. So then supposing if we are able to find a particular deadlock occurrence, then we need a way to recover it. Either we need to reboot the system or we need to pick a victim and terminate that particular thread. You would have pressed an Alt Control Delete button and you would have got a task manager. You would have seen a task manager. In the task manager, if you want to stop a particular thread, you need to click that particular thread and you need to click stop process. So it will be stopping that particular process. So it is a reactive approach of dealing a deadlock. If you are not stopping that process, your system will get into a deadlock, will end into a deadlock wherein the system will not be working again. So unless and until you stop that particular thread, it will not be working. That is called as, such an approach is called as a reactive approach. Then the second approach is called as the proactive approach. In the proactive approach, we have the deadlock prevention method. How to prevent the method? We have 4 necessary conditions for preventing a deadlock. Those 4 necessary conditions, we will be seeing it in the forthcoming slides. So as of now, let us consider there are 4 conditions to prevent a deadlock to happen. Then the other proactive approach is about the deadlock avoidance. How do we avoid a deadlock? So we need to carefully allocate the resources based on the future requirements, and when we are able to identify and allocate the necessary resources, then definitely a deadlock could be prevented. So this is said to be our second approach of dealing with the deadlocks. The third approach is we just ignore the problem. So how do we ignore the problem? Pretend deadlocks will never happen, assuming the deadlocks will not happen at all at any particular moment. Or the second approach of ignoring a problem is having an ostrich approach. What do you mean by an ostrich approach? An ostrich approach is, have you ever seen an ostrich? How does it look like? An ostrich has a very long neck. So supposing if there is any problem, what an ostrich does actually is that it immediately digs a hole on the sand, and then it keeps its head inside the sand. So what happens is that it pretends as if there is no problem at all. So after all the problem gets erased out, then it takes the head out of the sand. Such an approach we call it as an ostrich approach. So that has been described in this slide. So in the second point of the slide states it is to stick one's head in the sand and pretend as if there is no problem at all. So but this approach is pretty costly, and it allows the problem to occur than to attempt its prevention. Now we are going to see the necessary conditions for a deadlock. So I said in my previous slide that we have 4 different conditions for a deadlock to happen. The first condition is called mutual exclusion. Second condition is the hold and wait. Third condition is no preemption. Fourth condition is the circular wait. Now, what do you mean by a mutual exclusion? A mutual exclusion is that only one processor may use a resource at one particular instance of time. That is called as a mutual exclusion. What do you mean by hold and wait? As far as this hold and wait is concerned, processors currently holding a particular resource, it cannot be allocated to a different set of resource. So it has to wait until that particular resource gets available. So such an approach we call it as hold and wait. Then the third point is no preemption. No preemption means no resources can be forcibly removed from a process holding it. That means, say for example, your lecturer is handling a class. Somebody enters inside the class. So what happens? Immediately the lecturer sees him, and supposing if he is going to stop the particular lecture, then such a lecture you call it as preemption. Supposing if he is not minding whoever comes into the class, and if he is going to continue his lecture, then such a concept you call it as no preemption. That is, he will be continuing until he finishes the process, he finishes this work, he will not be stopping at all. So such a condition is called no preemption. And then the fourth point is the circular wait. Before we could go with the circular wait, let us have a small break, and then we will continue after the break. Welcome back, viewers. Before the break, we were handling certain topics. We were speaking about what a deadlock is, what were the types of deadlock, how a deadlock happens, and I showed you a real-time day-to-day event of how a deadlock happens as an example with respect to a traffic scenario. Then we saw the types of deadlocks. As well, we even saw the types of resources. Then I gave you an example with respect to an ostrich, and we call it as an ostrich approach. Then we went on to the necessary conditions for a deadlock to happen. So in which we saw 4 different conditions. Condition number 1 was mutual exclusion. Condition number 2, it was hold and wait. Condition number 3, it was no preemption. Condition number 4, it was circular wait, out of which we have explained the first 3 conditions, wherein in the mutual exclusion you will be having only one processor will be using one particular resource at a time, and as far as a hold and wait is concerned, processors are currently holding the resources granted earlier can request for a new resource. No preemption, I gave you an example with respect to a real-time classroom scenario, wherein if someone enters inside the class, how will the students behave or how will the lecturer behave? If he is not going to care about the person whoever is entering inside the class, and if he is going to carry out his lecture, then it means he is working out on a no preemption basis. If he is going to stop for a while, and if he is going to come out of the class and by giving way for the visitor to interact with the students, then such a condition you call it as preemption. Now we will be seeing about a circular wait. What do you mean by a circular wait? A circular wait is nothing but it is a closed chain of processes that exist in such a way that each process holds at least one resource needed by the next process in the chain. Now let us see the diagrammatic representations of each and every condition, necessary conditions, whatever we have seen. In the first one, it is about the hold and wait. Viewers, I suppose you might be knowing what does a mutual exclusion and what does hold and wait is. Now we will see what a hold and wait is with respect to a diagrammatic view. So now let us see in this diagram, this task A, it is holding a resource called resource number 2, and it is waiting for the resource number 1, wherein this particular resource number 1 is being held by this particular task B. So as of this particular moment, resource 1 is not available and it cannot be readily accommodated for this task A. So this task B in turn is waiting for the resource A, which is being held by task A. So this situation is a deadlock situation, wherein task A is holding one particular resource 2, and it is asking or it is waiting for resource 1, and this task B is holding one particular resource called resource 1, and it is waiting for this resource 2. So such a condition you call it as hold and wait deadlock, wherein we do not know how much time this particular task A will be holding this particular resource 2, or in other words, how much time this particular task B will be holding for this particular resource 1. So if you are not knowing the time instance, which means it is going to end in a deadlock situation. The second one about the no preemption. What do you mean by no preemption? Again, as I said, when a process is being held by a resource, so unless and until it completes that particular process, if that resource is not going to be left out, then such a condition we call it as no preemption. Let us look into this slide. As this example shows, this R1, this process P1, resource 1 is holding this process P1, and this resource 2 is holding this process P2, and this resource, now suddenly this process P1 enters into this resource 2, or in other words, it is being called by this resource 2. So unless and until this process 2 is being released, it cannot take into account the process 1 or the P1. So such a condition you call it as no preemption. So it is not leaving that particular process. So till it completes that particular process, this resource, it will be using that particular process and it will be waiting till it completes. So that is called as no preemption. Next is about the circular wait. What do you mean by circular wait? As far as a circular wait is concerned, let us consider this example in the slide. In this slide, in the circular wait, you have two different resources. Again, one is called the resource, one is named the resource X, other one is named the resource Y. So you have two processes. One is named process A, other one is named process B. So let us consider in this example this process A or this resource Y owns this particular process A. So it holds this particular process A. So this particular process cannot be used by other resources. So, and in the second condition, this resource X has also asked for this process A, but since this has been used by this resource Y, this process A is waiting for the resource X. Now, here in this condition, this resource B is being owned by resource X is being owned by this process B. So, since this is being owned by this process B, it cannot use this particular process B, cannot be used anywhere else, and this particular process B is waiting for the resource Y. Friends, as of now, this particular resource Y is being used by this process A and it is being owned by this process A. Unless and until this resource Y finishes its work, then only it becomes free and then only it can be accommodated to process B. Now, this kind of condition you call it as a circular wait, and you can compare this condition with the traffic diagram, with the second traffic slide diagram that we have seen, wherein all the cars will be placing over there and only the truck will not be in a position to move from one point to other. So such a condition you call it as a circular wait. This example of circular wait, you could relate it with the example that has been shown with respect to a traffic signal. In the traffic scenario, you would have encountered how a truck or a car was waiting in a queue, and supposing if any one of the vehicle needs to move out, it has to move, then only the other vehicle can roll upon. So that example you can see in the slide. Even you have the car, the buses has been waiting, and this car has been waiting for this car to move. So this car is waiting for this car to move. So this car in turn is waiting for the bus to move. So this is a very good example for a circular wait problem. So again I repeat, here this bus is waiting for this car, this bus is waiting for this car to move, this car in turn is waiting for this particular car to move, this car is in turn waiting for this particular car to move, and this black car is in turn waiting for the bus to move. So this is where a circular wait problem occurs. So how will it get resolved? It will not get resolved if it is going to move on a forward direction. So every bus and all these cars have to go in a reverse direction, or these things have to go in a reverse direction. So then only the traffic congestion may hold on. So this is called as a deadlock, a circular wait deadlock situation, wherein it is also common with this diagram, even with this photograph. Even in this photograph, this car could move only if this car and this bus moves out, and this truck could move only if these cars move out. So this is as well an example for a circular wait, for a deadlock situation. Now let us move on to the next topic called the deadlock detection. In this, how do we detect a particular deadlock? Because we need to be sure, before a deadlock occurs, we need to be sure how to detect and how to prevent that particular deadlock from occurring. So as far as this deadlock detection is concerned, in the slide you have the requested resources are granted to processes whenever possible. Periodically, the operating system performs an algorithm that allows it to detect the circular wait condition. A check for deadlock can be made as frequently as each resource request, or less frequently depending on how likely it is for a deadlock to occur. So this is how a deadlock detection has been seen in. Now, how do you test a deadlock? So there are different aspects of testing a deadlock. One way to find the cycles. So how do we find the cycles? What is the idea of finding the cycle? So this was a process people might have been waiting for but it wasn't waiting for anything else. Say for example, you have a node and with no outgoing edges. What do you mean by it? It is a circular edge wherein you have a node which has been in a circle wherein you do not have an outgoing node at all. So erase this node and also erase any edges coming into it. So this idea, it is what the people use it. And if and only if the graph has no cycles, we will eventually be able to erase the whole graph. This is as well called an algorithm called as a graph reduction algorithm. What is a graph reduction algorithm? A graph reduction algorithm is one wherein which does not have any sort of cycles in it. So such an algorithm, we call it as a graph reduction algorithm. So this is how we detect a deadlock. And now we will just move on to the next phase called the strategies for handling a particular deadlock. So as far as the strategies are concerned, the strategies are broadly classified into three groups. One is called as the strategy deadlock prevention, deadlock avoidance, and the deadlock detection. And after you detect a deadlock, what do you need to do? You need to recover the deadlock. You need to find a way how a deadlock should be recovered. After detecting, we have to recover it. Then only we can resolve from a situation of occurring from a deadlock situation. We can prevent a deadlock situation, right? So now as a first topic, we will see deadlock prevention. How do you prevent a deadlock? So deadlock prevention is, it prevents a deadlock by restraining a request made to ensure that at least one of the four deadlock conditions cannot occur. What were the four deadlock conditions? We saw four deadlock conditions. One was mutually exclusive, other one was hold and wait, third condition was no preemptive, fourth condition was circular wait. So in this, in order to prevent a deadlock, it should not, one of the four deadlock condition should not be occurring in order to prevent a deadlock. Now then next one is the deadlock avoidance. So in order to have a deadlock avoidance, it grants a resource to a process if the resulting state is safe. A state is safe if there is at least one execution sequence that allows all processes to run to completion. What do you mean by a safe state? A safe state is one wherein you do not have any sort of deadlock issues at all. You are completely sure of your process, you are completely sure of the resources, you are completely sure of the availability, you are completely sure of the need. So when you are so sure about everything, when you have ample amount of resources, then such a state you call it as safe state. So a deadlock will not occur in a safe state. So a deadlock may occur only when the state is said to be unsafe. Now the third point is about the deadlock detection and recovery. It allows deadlock to form, then finds and breaks them. Now we move on to this summary of whatever we have seen so far. We have studied what a deadlock in operating system is, and then we have seen the characteristics of a deadlock. We have seen the different types of deadlock. I suppose you might be remembering the two different types of deadlock, and then we have become confident enough in dealing with the deadlocks. We have as well studied the conditions required for a deadlock to happen, and then we have also learned of how to detect and how to test a particular deadlock situation. Now let us pose our understandings from the session whatever has handled now. As far as the session is concerned, we have certain questions to be asked. The first and foremost question is, what is a deadlock in operating systems? Second question, mention the characteristics of a deadlock. Third, what are the types of deadlocks? Fourth, how to deal with deadlocks. Fifth, what are the necessary conditions for a deadlock to happen? Sixth, how do you detect and test a particular deadlock situation? With this, we will conclude this session. Remaining topics we will see in the consequent section. Thank you.